Today we're going to walk through the solving of an unknown structure based solely on the NMR spectra, and in particular with a major assist from 2D spectra from COSY and an HSQC spectrum. And we're going to pretend for a moment that our situation is simply this. We have this mysterious white powder, and we don't know anything else about it. It's not like we're a synthesis project and we kind of know what we were trying to make and what we started with. It's not like we're doing a natural product extraction where we have a decent idea of what it is we're trying to separate away. What we have is simply this mysterious white powder, and we're not even going to have the advantage of doing any mass spectrometry or knowing molecular weights. All we know is it's a mysterious white powder and it's going to dissolve in a little bit of chloroform. And so, strictly NMR spectra. And as we are doing this, the spectra that we see here, a link to them is on the description to this video. It's usual. I think it's a really good idea to have a copy of these in front of you, and when you see see vertical lines being drawn on the computer graphics or something. If I was doing this on paper, heck, I've got a ruler, I'm drawing these lines and stuff. It's really useful. It kind of helps make this a little more active learning in this kind of online video experience. It's sometimes difficult to reproduce. I strongly urge you to do that, to kind of draw along on a copy of the spectra, what you see me doing here, because it really, I think, helps tie together what we're talking about, and it gets you kind of actively seeing some of these correlations for yourself. So give it a try. As always, we take a look at the proton spectrum first, and we see it's an interesting spectrum. It's got some interesting stuff going on in here. We're going to first look at the downfield side, and we see a couple of things out here that are very distinctive and should just jump right out at us. Up here, near 12 ppm, we see a very broad peak, almost lost in the baseline. But it integrates to 1. This is the dead giveaway of a carboxylic acid in chloroform solvent. We confirm that, of course, by looking at the carbon spectrum, and we see definitely a carbonyl at 182 ppm, exactly the position we would expect the carbonyl of a carboxylic acid. So right there, from just that, we have a significant piece of this molecule. Certainly not all of it, but we have a significant fragment a significant puzzle piece that we can put aside and eventually incorporate it into our structure. We also see a very nice aromatic region right here in the classic aromatic region between 7 and 7.5 ppm in the proton spectrum. And in fact, it's a lovely area. It integrates 2 and 2, 4 total, indicating that it's almost certainly a di-substituted benzene ring. The symmetry of it, leads one to think in a di-substituted case, ortho, meta, or para. Para is the most symmetric, and the proton spectrum is nice and symmetric. So it makes us think about that. But of course, we want to try to confirm that, and so we look at the carbon spectrum. And what we see in the aromatic region of the carbon spectrum are 2 CH peaks and 2 quaternary peaks, 4 total. Only the para structure, where the 2 substituents, here labeled with simply the letters A and B, are not equivalent to each other. Okay? That is the only structure that would produce these proton and carbon NMR results. And so we have another significant fragment of the molecule right away to put in our collection of puzzle pieces as we try to put this thing together. And now our attention focuses on the upfield side, on the aliphatic region. Because none of these peaks are, have the chemical shifts consistent with alkenes. They all seem to be coming from things that are just singly bonded, classic aliphatic peaks out here, with some lovely coupling patterns. And in fact, to be honest with you, a really careful analysis of the coupling patterns would probably be sufficient to put this structure together. But what I want to really introduce you to here is using the COSY spectra and ultimately the HSQC. Is these spectra for students, they tend to be, especially COSY, they take a little bit of getting used to. And this is a classic example of how a COSY spectrum can really tell you a lot of information here in an example molecule that is, not hugely difficult, not too terribly simple either. And so the COSY spectrum is the one we're going to spend quite a bit of quality time on. So here it is. And remember, a COSY spectrum is simply a homonuclear correlation. It's designed to tell us which protons a group of protons is coupled to, which means which protons are next to each other in the molecule. Walking through the process of analyzing a COSY spectrum, it's almost always critical that you have a place that you're very certain about, or as certain as you can be with an unknown. And by that I mean a resonance that we're pretty certain about here. For our purposes, it's going to be this group up here that integrates to 6, which is an unusually high number, and it is at 0.95, less than 1 ppm, indicating a methyl group, in fact indicating 2 equivalent methyl groups at the end of an alkyl chain. And so we're going to begin with that assumption, that this molecule has 2 methyl groups that are equivalent to each other. And in other words, 2 methyl groups likely attached to the same carbon. So this is a fragment that we have that we're going to run with for a moment, is a carbon with 2 equivalent methyl groups on it. And we're going to try to use the COSY spectrum to tell us what else is near this group of protons, this equivalent group of methyls. So here's how we do it. On the COSY spectrum, and I usually will start here at the top, we find the resonance of our 2 equivalent methyl groups, the one that integrates to 6, and here at slightly less than 1 ppm. We draw a vertical line down from that resonance. Now we come to the diagonal. That's fine. Diagonals are nice, but remember, they tell us no new information. They simply tell us that the methyl group appears on both axes. That's really not relevant. So I keep drawing my vertical line until I actually hit a real crosspeak, and I do. I hit it right here. What you do then is at the crosspeak, you turn 90 degrees and you go toward the other axis. And when you do that, you find yourself at a resonance that integrates to 1. We seem to have found 1 proton that the equivalent group of methyls is coupled to. And it's not a huge surprise. That group of equivalent methyl groups that integrates to 6 is itself a doublet, implying that it has 1 proton as a neighbor. Now by doing this in the COSY spectrum, starting at the position we know, going to the crosspeak, turning, and then moving to the other axis, in a sense, what we have done is essentially jumped from a position we knew to a position we now know very well. The single proton must be a CH group that is coupled to the 2 equivalent methyl groups. Okay, so we've moved one carbon-carbon bond further into this molecule, gone from 2 equivalent CH3s to a CH group. So we've expanded our known pieces a little bit, and we've taken a step further into the molecule here. And we look at the resonance of this CH. We look at it on the proton spectrum, and sure enough, it looks something like a septet when we look at the full proton spectrum here. And it's not a huge surprise. Back over here, there are 6 equivalent protons. 6 equivalent protons would split this signal into a septet. Okay, so it's it's kind of consistent here that this is where we've ended up. Now the next question is, can we take this step? Can we go another step? Can we use the COSY to find any more protons? And so now we take this position as our known position. We know this CH group. Can we use the COSY to step to the next carbon? Is there some group of protons over there that this is coupled to? So what we do is we take this septet, or what we believe at the moment is a septet, and we draw our vertical line. Now we do come to a cross peak even before we get to the diagonal, but this takes us back to the equivalent methyl groups, okay? It takes us right back to where we came from. It's a nice cross peak, but it does not give us any new information. So we're back here. We ignore this cross peak, come to the diagonal, and then continue moving, seeing if we come to a new cross peak. And we do. We come to a new cross peak that we have not examined before. What we have done then is found that this CH proton, which has these six protons from the two equivalent methyl groups over here, is also coupled to a CH2 group. We look at this resonance. It integrates to 2 in the proton spectrum, and it is itself a doublet. So we have found a third member, or third group that these protons are all coupled to. And that has a significant revision of our interpretation of our septet. It's not a septet. It can't be. Think about it. Over here, 6 equivalent protons. Over here, 2 more protons, the CH2 group, that the COSY tells us this is coupled to. In other words, this single proton has 8 neighbors. It must be not a septet, a nonet, split into 9. Now that's a little bit hard to see on a standard presentation of the spectrum on paper or on the computer screen unless you can examine it very carefully. Expand it on the computer screen. We can. Here it is. And in fact, oh my gosh, it is a nonet. There are 9 peaks here. And if you go to the 9th row of Pascal's triangle, 1, 8, 28, 56, 70, 56, 28, 8, 1. I think I got that right. It is a nonet, a gorgeous nonet. And the COSY spectrum is what really keyed us in. There is something interesting here. So what we have is essentially a spin system, is the phrase used, built from 3 groups. The 2 equivalent methyl groups, coupled to the CH group, coupled to the CH2 group. Okay? This is the spin system so far. Now we ask one more question of the COSY. Does the CH2 group have anybody else over here? Can we step one more group into the spin system? We pull up the COSY one more time. We now go to this position as our known position. We drop our vertical line and we start looking for cross peaks. Now, we see cross peaks that take us back to the CH group, but no new cross peaks. There's nothing new here. That means, therefore, that the CH2 group is not coupled to anything else. Now, there may be carbons over here. There's no doubt about that. But those carbons have no protons attached. We are not coupled to anything else beyond the CH2 group. So we have mapped out the complete spin system. It's an isobutyl group. 2 CH3s, CH, CH2. And then a bond, okay, we can't forget that each of these carbons is going to have 4 bonds, a bond to something else. We have mapped out a significant fragment of this molecule. So we add this to our collection of puzzle pieces. And it's back to the proton spectrum. We are not done yet. We realize there are a couple of other resonances that we have not accounted for yet in our examination of the COSY spectrum. There's a methyl group, and this methyl group is split into a doublet. It integrates to 3, so it's a single methyl group. We pull out the COSY spectrum and we do the same thing again. Now, this methyl group is the position we know. We drop down the vertical, we find a crosspeak. There is a crosspeak. We go to the other axis and we find that we are now at CH group, a different CH group than we were examining a few moments ago. And in fact, this is the last resonance we have not accounted for on the proton spectrum. Indeed, this CH group is a quartet. 3 neighboring hydrogens over here, quartet, no neighboring hydrogens over there. And in fact, the COSY indeed shows that there are no further crosspeaks. A second spin system, a simpler spin system, CH3CH. Now, this carbon, the CH carbon, has to have its total of 4 bonds, so it must be connected to 2 other things, neither of which is a carbon with a proton attached. And that accounts for all of our puzzle pieces. And so now, with this collection of puzzle pieces, we are now tasked with putting this entire molecule together and not violating any chemistry rules as we do so. And yes, there is only one reasonable molecule that we can put together from these pieces, and it is our dear friend ibuprofen, okay? One of my favorite example molecules. It is a sophisticated molecule, not terribly, not hugely difficult, not terribly easy, kind of sits right there in the middle. And the COSY spectrum is really powerful. It really shows what kind of power a COSY spectrum has in helping to map out the spin systems, particularly the aliphatic spin systems of this molecule. Now, I've done an earlier video on the carbon spectra of ibuprofen. It turns out there's actually a challenge in the ibuprofen carbon spectrum. It will turn out 2 of the carbons are completely overlapped in that molecule. And so when you count the number of carbon peaks versus the number of distinct carbons you should see in the molecule, it appears you're missing one. Carbon and the depth spectra, which was the focus of the previous video, reveal that the overlap signal, which is this one right here, is actually a CH and a CH2. It just happen to be right on top of each other in the carbon spectrum, which is interesting, but the depth spectra reveal it. The heteronuclear correlation, the HSQC spectrum, also shows this very nicely. And HSQC spectra, remember, what they will tell us is which proton is connected to which carbon. And so we have a proton axis and a carbon axis. I'll show you the way it works. It's actually simpler in some respects to use than the COSY spectrums. We don't have the diagonal in an HSQC like we do in a COSY. But the interpretation of it is very similar. For example, here is the group of equivalent methyls, the group of 6 2-methyl groups, 6 total, that integrates to 6. That doublet, the 2 methyls at the end of the isobutyl chain. If we, on the HSQC, draw our vertical line until we come to the crosspeak, and once we're there, we turn and go now to the carbon axis, we see here is the carbon signal that the carbons of the 2 equivalent methyl groups. It tells us which carbon is attached to which set of protons. The interesting one is that carbon that the depth 135 reveals is actually 2 signals. Here it is. Here's the carbon, and what we're going to do is start on the carbon and draw our line, this time a horizontal line, until we come to a crosspeak. But if you notice carefully, you come to not 1, you come to 2 very widely separated crosspeaks. In other words, this one carbon signal is correlated with both this CH and that CH2. The HSQC confirms what the depth 135 showed us, that this one carbon signal is indeed 2 separate carbons, a CH and a CH2. And in fact, in mapping out the spin systems like we did in the COSY, it shows us that it's actually the CH of this spin system and the CH2 of the isobutyl spin system. So in other words, the two carbons that are right over the top of each other aren't even members of the same spin system. They're on opposite sides of the molecule. It just seems to be pure coincidence that these two carbons are right on top of each other in the carbon spectrum. HSQC, just like DEP 135, makes that abundantly clear. Together, I hope that this shows you a little bit about how to use COSY and HSQC to learn more about molecules. They are, on modern instruments, fairly easy to obtain. They don't take terribly long. To be honest, I think they're a little underused in teaching students about the power of NMR and what it can do for us. They are marvelously useful experiments very often in putting together structures of unknowns or confirming structures of molecules that we think we've extracted or think we've synthesized. Hope this helps. Take an opportunity to practice a few of these, and talk to you later.